FET Self Bias Configuration. The Self Bias Configuration eliminates the need for two DC supplies. Unlike the fixed bias configuration, this doesn't have a VGG connected on the circuit. So the controlling gate to source voltage is now determined by the voltage across the resistor RS, which is connected on the source terminal of the circuit. So in doing so, the DC analysis of this configuration, again, the capacitors are replaced with open circuit, or yes, open circuit, and the resistor RG as well is replaced by a short circuit, since IG is equal to 0 amperes. So the resulting DC equivalent circuit is like this. So the current through RS is a source current IS, but IS is equal to ID. So the voltage across RS is equal to, by Ohm's law, ID RS. So for the indicated loop here, in this direction, we will take KVL. So we have a negative VGS minus VRS equals 0. So our VGS is equal to the negative VRS. So VGS is equal to a negative VRS, where VRS is equal to ID RS. So VGS can be computed with this equation, negative ID RS. The self-bias configuration by mathematical solution also uses the Shockley's equation to solve for the ID of the circuit, which is equal to IDSS 1 minus VGS VP, the quantity square. But if we will substitute this equation of VGS on the Shockley's equation, our resulting circuit will be like this. IDSS 1 minus negative ID RS all over VP squared. So we further simplify the equation. So IDSS 1 plus ID RS all over VP, the quantity square. So this will be the other formula to get the value of ID in this configuration. Also, to solve for the other parameters, taking a look at the drain to source direction here, okay, we have a VDD minus VRD minus VDS minus VRS equals 0. So in this equation, we can solve for the value of the VDS, which is, if we will transpose the other terms, this will give us VDD minus VRD minus VRS. Also, the Yes, the VDS can be further simplified with this equation, VDD minus ID times the value of RD plus RS, because we know that IS is equal to ID. And to get for the value of VS, VS is equal to ID RS, and VG for FET is equal to 0 volts, and to get for the value of VD, that is equal to the VDS plus the VS, or VDD minus VRD. So here are the different parameters of the FET. So to further understand the self-bias configuration, let's take this example. So we are to determine the following for the given network: the VGSQ, IDQ, VDS, VS, and the VD. So using the mathematical approach, okay, so ayan. So A, VGSQ. So how do we get the VGSQ? So a while ago, we are given with this equation, our VGS is equal to the negative ID times RS. We will make this at IDQ and VGSQ because they are taken at its, or they are the quiescent values of the given circuit. So VGSQ, there, ID is not given, so RS is given. So VGSQ is equal to negative IDQ times 1 kilo ohms, or so ayun. So mahihirapan tayong isolve yung problem kasi this is a one equation to unknown. So we need to find a way to get the value of the VGSQ. So what do we need, or what we will use to solve the problem? So we will use the Shockley's equation. Okay. Our IDQ is equal to IDSS 1 minus the original Shockley's equation, VP, the quantity squared. So we will use this equation. How? By substituting, okay? So we will express this in IDQ as negative VGS all over 1 kilo ohms. So we will substitute this equation to this Shockley's equation here. So we will have a negative VGS Q all over 1 kilo ohm is equal to, IDSS is given equal to 8 milliamperes, 1 minus VGS all over VP is given, that is a negative 6 volts squared. So we now have a one equation, one unknown here. So we can solve for the value of the VGSQ. So by quadratic equation, Okay, using our calculators and finding the value of x, so we will be able to get two roots for the given equation. So the possible values of our VGS, first is 2.588 volts and the other one is negative. So the other one is negative 13.912 volts. Since the value of the VGS cannot be greater than the pinch of voltage, negative 6 volts, so we will disregard the second value of the VGS. So we will disregard this and accept the value here. So our VGS will be equal to, our VGSQ will be equal to negative 2.588 volts. So this will be our answer. Now for the value of IDQ, okay, so we will use this formula since VGS is already solved. So negative 2.588 volts all over 1 kilo ohm, giving us a value of IDQ equal to, yes, 2.588 milliamperes. For the next one, we will take a look at the DS loop to get for the value of VDS, KVL at DS loop, VDD minus VRD minus VDS minus VRS is equal to 0. So substituting the given values, 25 volts minus VRD is not given, VDS and minus VRS is also not given. So take note, this equation can be expressed like this: VDS minus ID RS plus RD. Okay, so equals 0. Since we are after the value of VDS, so our VDS is equal to 25 volts minus IDQ is already computed, 2.588 milliamperes. RS is given with the value 1 kilo ohm plus a 3.3 kilo ohms. So our VDS will be equal to 13.87 volts. Next is VS. So for the value of VS, VS is simply equal to ID, RS. Tama. So VS, substituting the value of ID, 2.588 milliamperes, 1 kilo ohm, our VS is simply equal to 2.588 volts. Next is our VG. VG is simply equal to 0 volts. And for the last one, our value of VD is equal to VDS minus VS. VDS is already, we had already computed for the value of VDS, 13.87 volts minus our VS of 2.588 volts, giving us a value of our VD equal to 11.284 faults.